Have you ever wondered how AI really learns? I mean, what's actually going on under the hood? Well, it's not magic, and it's definitely not some unknowable black box. It's an engineering process, a structured step-by-step journey. And today, we're going to walk through that entire life cycle together. We're going to start with just a simple spreadsheet of raw data and end up with a system that can make genuinely intelligent decisions. So let's get started.
All right, here's the roadmap for our explainer. First, we're going to break down the basic anatomy of data itself. Then, we'll dive into the prep work, which is absolutely critical. From there, we'll tackle the incredibly deceptive overfitting trap, learn how to properly grade a model's real performance, and then we'll wrap up by exploring two super powerful strategies for building a committee of experts, one called bagging and the other boosting.
You know, every great building starts with a solid foundation. And for machine learning, that foundation is and always will be data. So before we can even think about teaching a machine anything, we have to learn to speak its language. And that language is built on just a few core, really simple ideas.
To you and me, data is everywhere, right? It's a photo, it's a song, it's the words I'm saying right now. But for an algorithm to find patterns, that data has to be organized into a really clean, structured format, basically a big spreadsheet. This structure is the key that unlocks a machine's ability to learn. So let's break down the three core parts that make it all work.
First up is the concept. This is just the goal. It's the what we're trying to teach the machine. It's the main question we want answered. Is this email spam or not spam? Is this credit card transaction fraud or legit? The concept is our target. Simple as that.
Next, we have instances. Think of these as the individual examples or the case studies. If our concept is spam, then one specific email is an instance. In our spreadsheet, each row represents one self-contained instance for the machine to study.
And finally, we have attributes, which you'll also hear people call features. These are all the descriptive details for each instance. For our email example, attributes would be things like the sender's address or the number of exclamation points. These are the clues the machine is going to use to try and solve the puzzle.
So, we've got our concepts, instances, and attributes. Seems pretty straightforward, right? Well, here's the catch. Real-world data almost never, ever looks this clean. Getting it into that perfect spreadsheet format is a massive job, a process we call data preparation. And honestly, this is where most of the blood, sweat, and tears of a project happens.
And this step is totally non-negotiable. It's like a master chef can't make a gourmet meal with dirty, disorganized ingredients. In the same way, an algorithm can't learn anything useful from messy data. This prep work, the cleaning, the organizing, the structuring, it's everything. In fact, some people estimate it can take up over 60% of a project's total time.
Which brings us to probably the most common challenge in all of data prep. The crucial information we need is almost never in one convenient place. It's usually scattered across multiple, related tables. Think about a customer database. You might have one table for their purchases, another for their addresses, and a third for their support calls. To see the whole picture, you've got to bring it all together.
Okay, let's make this super concrete with a classic example. Let's say we want to teach an AI the concept of sister. Our first set of clues is in this table. It's a simple family tree that tells us who a person's parents are. It's helpful information for sure, but it's not the whole story.
Our second set of clues is the target concept itself. A table that lists pairs of people and whether the answer to is person 1 the sister of person 2 is yes or no. Now here's the problem. For an algorithm, these two tables might as well exist in separate universes. It just can't see the connection between them.
And here is the magic moment. We perform what's called a join operation, sometimes we call it flattening the data, and we create one single wide table. Now look at this. For any given pair of people, the machine has all the clues it needs on one single row. Their names, their genders, their parents, and the final answer. Now it finally has a pattern to look for.
Okay, one last, quick but important point on data prep. The type of attribute really matters. The machine needs to know the rules of the game for each column. Is it just a label, like sunny or rainy? That's called nominal. Or does it have a meaningful order, like cool, mild, hot? That's ordinal. And does 0 mean nothing, like it does with distance, or is it just another point on a scale, like with temperature? Knowing this stuff is crucial because it determines what kind of math the algorithm is even allowed to do.
Okay, so we've prepped our data, we've fed it into a learning algorithm, and voila, our new model is getting a perfect score. Success, right? We can pack up and go home. Or can we?
We've just walked right up to the edge of the single most common and deceptive trap in all of machine learning. It's called overfitting. This quote just gets right to the heart of the matter. A model's performance on the data it studied can be, and often is, wildly, hopelessly optimistic. It's like a student who aces the practice exam. Does that mean they're ready for the real final? Not necessarily. They might have just memorized the answers to the practice questions. And this brings us to the absolute critical difference between memorization and true learning, which we measure as training error versus test error. Training error is like giving a student an answer key before the test. Yeah, they'll get 100%, but did they actually learn anything? Test error, on the other hand, is the real deal. This is when we grade the model on a completely separate set of data it has never, ever seen before. This is the only true measure of how it's going to perform out in the real world. So the whole idea is to hold back some of our data for a final exam. But that creates a tricky dilemma. See, the more data we use for training, the smarter our model can become. But the more data we hold back for testing, the more reliable our final grade will be. So what do you do when your data is limited? Well, the solution is a truly elegant technique called tenfold cross-validation. It's a way to kind of have our cake and eat it too. We break our data into 10 chunks. We train on 9 of them and test on the one we held out. Then we rotate. We pick a different chunk to be the test set, train on the other 9, and test again. We do this 10 times until every single piece of data has had a turn being in the test set. And by averaging those 10 results, we get a much more stable and trustworthy score for our model. But even with a reliable score, just counting the number of mistakes isn't enough. We need to understand the kind of mistakes our model is making. And this simple box, called a confusion matrix, shows us the 4 possible outcomes. We can be right in 2 ways, true positives and true negatives, but we can also be wrong in 2 very, very different ways, false positives and false negatives. And that distinction, well, it's absolutely critical.
And here's the so what moment. Think about a medical diagnosis model. A false positive means telling a healthy person they might be sick. Now that causes anxiety and it means more tests, but it's manageable. A false negative, on the other hand, means telling a sick person that they're perfectly healthy. That could be a catastrophe. By understanding the real-world costs of these different errors, we can build models that are not just accurate, but also responsible and safe.
This chart shows that trade-off perfectly. You see, Model A is aggressive. It's great at catching the yes cases, but it pays a price. It raises a lot of false alarms. Model B is more conservative. It has far fewer false alarms, but it might miss some of the real cases. So, which model is better? Well, there's no single right answer. It all comes back to the real-world cost of each type of error for your specific problem.
Okay, so far, we've been focused on building and grading one single model. But what if one brilliant mind isn't the answer? What if the secret to top-tier performance is a whole team of models? This powerful idea is called ensemble learning, and frankly, it has revolutionized the entire field.
We're going to look at the 2 most famous strategies for this. First is bagging. You can think of this like assembling a diverse team of independent experts who all work in parallel and then vote on the final answer. The second is boosting, which is more like building a specialist team sequentially, where each new member is hired specifically to fix the mistakes of the last one. Let's start with bagging. The whole secret is in step 1, sampling with replacement. Okay, imagine you have a bag with 100 unique marbles. To create a new training set, you pull out a marble, you note its color, and then, and this is the key part, you put it back in the bag. You do this 100 times. Your new set of 100 marbles will have some duplicates, and some of the original marbles won't have been picked at all. We just do this over and over to create lots of slightly different training sets, build a separate model on each one, and then let them all vote.
So what's the point? What problem does this actually solve? Well, it tackles something called variance. Some algorithms are a bit, let's call them unstable or jittery. If you just change a few data points in their training set, you can get a radically different model. They can get superstitious about weird quirks in the data they happen to see. Bagging fixes this. By averaging the opinions of all these different models, it smooths out those instabilities and makes the final prediction far more reliable.
All right, now for boosting. If bagging is all about the wisdom of crowds and democratic voting, boosting is about focused, obsessive, iterative improvement. It's a method designed to build a chain of specialists, where each new model is an expert on the cases the existing team finds the most difficult.
Here's how it works. In round 1, every single example in our dataset is equally important. They all have the same weight. We train our first simple model, then, oops, it gets this highlighted one wrong. Now just watch what happens next.
Before we build our second model, we completely changed the rules of the game. We dramatically increased the weight of the instance we got wrong, and we decreased the weights of all the ones we got right. So now, when we train model number 2, it has this massive incentive to get that difficult instance correct. It's being forced to focus on the first model's failures.
And this cycle just repeats again and again and again. Each new model is trained on a reweighted version of the data that basically shines a giant spotlight on the mistakes of the models that came before it. This creates this powerful chain of specialists who, together, cover each other's weaknesses and can solve incredibly complex problems.
And this is the absolute magic of boosting. You don't start with a brilliant, complex algorithm. You start with what we call weak learners. These are models that are incredibly simple, maybe just barely better than flipping a coin. But by forcing them, one by one, to obsess over each other's mistakes, you combine them into a single, strong learner with stunningly high accuracy. It's a true case of the whole being far, far greater than the sum of its parts.
So, when you look at the whole process, you see that building intelligence isn't about one giant magical leap. It's about careful structure, it's about rigorous and honest testing, and maybe most importantly, it's about having a systematic process for learning from your mistakes. It's not just a recipe for artificial intelligence, it's a powerful blueprint for any kind of learning. And it really makes you wonder, if this is how we build intelligent machines, what can it teach us about improving our own?